Okay, so our second speaker for the first session in the morning is my friend Roberto Serra from the University Federal from ABC. Yeah, so he's going to talk about non-classical advantages and fundamental limits in quantum thermodynamics. So
Yeah, thank you. I'm gonna talk about some experiments in this area, and my alma mater is also São Carlos. I don't have any work in collaboration together with Vitor, but I remember that when I was a student there, we had some discussions about physics, in particular about dynamic invariants, and I used dynamic invariants sometime after such conversations. And happy birthday, Vitor. The last time that I was in Brasilia, it was just in the beginning of the pandemic in Brazil. I was in a examination board for admission of new faculty members here, and it was completely crazy because in Brazil they start to do the lockdown, and we had a lot of uncertainties. So I'm very happy to be here again after the pandemic. It's really nice. Okay, so I'm from this university with this very funny name. I know the ABC means very basic as well, but this means that region in São Paulo metropolitan area composed by these three cities, Santo André, São Bernardo, and São Caetano. That's why ABC. And this is only 17 years old university. This university was created with a lot of missions. One of them was to contribute very decisively to the technological and scientific development in Brazil. And we believe that we are going the right direction because this university is among the 15 best young universities in the world, universities with less than 50 years. We are number 27, and we hope to increase a little bit. That region is a very industrial region, and with it is among of the biggest GDP regions in Brazil. So we have a lot of responsibility in that region. So as Marcus said yesterday, and Marcus also agreed with me that he forgot to mention that when quantum optics starts in Brazil, we have this Rio de Janeiro school and also this São Paulo school. And we have just one experimental group that starts to do experiments with single photons in Minas Gerais, and they start a single photon source in the 1999 decade, but more or less 25, 30 years ago. So we start experiments in quantum optics very recently in Brazil. Okay, and now we have several groups working on quantum information, but all of these groups originated in these quantum optics in groups in São Paulo and also in Rio and also in Minas Gerais. And we have this kind of network, and our plan is to spread around the country. In every state of the country, we'd like to have a group working on this kind of subjects. These are a kind of a cloud of our network, a word cloud with some of the words that appears in the papers. We always have something quantum. Okay. I will take the advantage of Lucas and also Marco's presentation because they already motivate why we are interested in this stochastic thermodynamics at quantum scale. But I will try also to answer some open questions that appeared in the previous presentation and show to you several experiments where we can test and prove such kind of ideas. For one side, we are interested in see how the emergence of the thermodynamic, how the thermodynamic laws emerge from quantum mechanics, and it is different from statistical mechanics because we are interested in the dynamic process very far from equilibrium. So we have to deal with a very far from equilibrium, and also we'd like to have a theory that could be relevant for just one particle. Yes, we can do thermodynamics for just one particle because we have repetitions, several repetitions, and then we have a statistical distribution. We can, as we can define a temperature, effective temperature for a Brownian particle, when we repeat the experiment several times, we can define everything for a single quantum system. And actually, we already did it when we treat an open quantum system, but now we are going further. From the other, on another direction, we can also use quantum features to get some advantage in some thermodynamic tasks, like cooling, work extraction, or any kind of control that we need to do in that kind of system. My motivation in that area is associated to the fundamental limits of quantum technology. In the same way that thermodynamics introduce limits to classical technologies, this will also introduce limits to the quantum one. And to understand the limits of the quantum technology, we have to advances on how we measure work heat dissipation at that scale. There is this working group in IEEE, the Institute for Electrical Engineering, trying to establish standards to measure energy consumption in quantum computers, for example. We know how to do it in classical computers, and we have to agree about how we will do it in quantum technology in order to estimate the energetic cost of such a technology. And of the experiments will be the Occam's razor for any definition of work, heat, and dissipation. So if you want to convince the people that we have a definition which is important and should be used, it's important to propose an experiment to test it, because heat is the amount of energy that we are dissipating to the environment. So if you can measure it, we can see if this definition makes sense, right? And I will show how to do it, at least in a system composed of qubits. About the quantum advantages that we can have in thermodynamic tasks, here I have some examples. All of them are related to experimental papers. For example, we can use the back action of a quantum measurement to extract energy. And then using this, we can reach unit efficiency with finite power, which is impossible in the classical regime. And we can also build Maxwell diamonds in the lab because we have control of the microscopic system. So we can really challenge the second law. And we can also use non-classical correlations to, for example, revert the heat flow of a system. And we have several applications of this in cooling of a quantum processor or a quantum sensor, and so on. We can also use, for example, dynamic invariants to find a shortcut to the adiabaticity, and we can avoid the friction at the quantum scale. This journalist wrote this about some works that was presented in a conference a few years ago. But we also have a very hard limit, so we can challenge the second law a little bit, and I will try to convince you that we can go a little bit further than the second law in the quantum system. But the third law seems to be a very hard limit to quantum technology. And here I have two examples. For example, if you admit the third law of the thermodynamics, you reach in the conclusion that it's impossible with finite resources to perform a perfect projective measurements. We cannot do projective measurements in the lab. We do something very similar to a projective measurement, but we never reach a perfect one. And if you admit the third law, it will be impossible. And also, when we prepare an initial state of a quantum computer, we have to prepare, if you want to prepare memory in the ground state, we have to prepare a zero temperature state. And it is impossible according to the second law, due to the unattainability principle. And depending on how close we are from the zero, this will produce a kind of an infidelity in a gate array, in a quantum algorithm with a given depth. And we will have a kind of a scale for the fidelity depending on the number of qubits that we have. So in that paper, this author showed that the Higat quantum computer follows this black solid line here. So it's almost impossible to reach 1,000 qubits with the with with the initial state preparation that they have now. The fidelity will go to zero. So I will also talk about a kind of a verification of the third law. And this is our quantum PlayStation that we use to have a lot of fun with this quantum. I use it to be a theoretician, and then about 12 years ago, I started to enter in the lab and to have a lot of fun. But I also work in theory also, and now I don't know what I am. I'm in a kind of a superposition state. So we are using nuclear spins as qubits, so we can choose different molecules, and we can have a different number of qubits. In our lab, we can reach up to 6 qubits. This technique is not scalable to build a huge quantum computer, but this is very nice to produce fundamental test of principles. So we introduce our molecule of interest in a solution. It's very diluted, like just 1% of the molecule that we are interested in. And we introduce it in a huge magnetic field, about 12 Tesla in our case. And the Zeeman resonance frequency for the hydrogen nuclei is about 1500 megahertz. And for example, for the carbon-13, we have 126 megahertz. For the fluorine 19, 407 megahertz, and so on. We can choose different isotopes in our molecules, and we can also prepare different molecules with different isotopes to produce a kind of a molecular quantum simulator. And we use a solution with deuterium, and we use the deuterium just to lock the field on resonance. Okay, so this is the photo of our lab, and we have a Hamiltonian there. We can neglect the interaction between different molecules because our solution is very diluted. Inside of the molecule, we will have the Zeeman interaction with the huge magnetic field produced by this superconductor solenoid. And this resonance frequency will be a little bit shifted. The shift is named as the chemical shift due to the electronic cloud and depends on the chemical bound. So that's why we can identify different qubits with the same kind, with the same isotope in a molecule, depending on the position of the atom in a molecule, the resonance frequency. And we also have a coupling between the different nuclear spins, nuclei. And this coupling can be described like this expression here with this tensor. And depending on the symmetry of the molecule, this coupling could be something similar to a Eisen model or a Heisenberg model, or depending on the if you have spin 1/2, if you have spin 3/2 and 7/2, we also have some nonlinear terms. And we also can switch on and switch off a radio frequency field on resonance with different nuclei. And we can switch on and switch off a term like this in the Hamiltonian with a time dependence. And we can also change the phase, so we can produce rotations on the plane. And this is one kind of a control that we can do with these modulated pulses. Here we have 3 qubits, and this is an experimental data of a stroboscopic quantum state tomography along the evolution of these modulated pulses. And we have to optimize these modulations in order to obtain very precise rotations. For example, we are also using machine learning strategies in order to decrease any experimental error in the manipulation. And typically, And now I'm back into a 2-qubit molecule. Typically, we have one of the qubits is encoded in the hydrogen, another one in the carbon 13 of that molecule here. And the typical decurrency times that we have in that system is about seconds. For example, the energy dumping time at T1 is about 18 seconds for the carbon. And here we have the dephasing time. The typical time for performing a pi over 2 rotation, for example, in that molecule is about microseconds, 10 to minus 6 seconds. So I can perform a lot of operations during that time. And the initial state preparation is a high fidelity operation that we have in that system. This is a kind of PUC sequence to prepare an initial state. We perform rotations, let the system evolve through this the scalar coupling, the Ising Hamiltonian, and then we can also control field gradients, which are controlled the phasing, and then we can prepare initial state like this one. For example, this one is the Werner state with some controlled noise here. We can add identity in a controlled way. We can reach fidelities like this, 0.9997. We are working to improve it. So let's go to the quantum thermodynamics. And when we perform an operation or when we look for the energy dissipation, that system, as the system is small and as it could be very far from an equilibrium, and also we have to encompass the native randomness of quantum mechanics, work, heat, and entropy production, for example, become stochastic variables with given distributions. And the entropy variation of the system is equal to the heat that the system exchange with the environment plus this entropy production, even out of equilibrium. Okay, this is the out of equilibrium. The entropy production is the out of equilibrium signature of the dynamics. And the second law could be stated as entropy production is always bigger or equal to zero. And the entropy production can also be written in terms for just a driving process where we change the Hamiltonian and let the system thermalize with the environment, in terms of the work minus the variation of the Helmholtz free energy. So this is a kind of the work that we dissipate when we want to extract or put energy in the system. And the efficiency of any cycle will be limited by a function of this entropy production. Depending on the cycle, well, this function will be different, and we can compute this function in several situations. And the work, as Marcus Arad told you, is associated, this work distribution, the mean value of work, is associated to different roads that we can take from the spectrum of the initial state in the spectrum of the final Hamiltonian, for example. And we have possibilities to have transitions depending on how we change the system. We can do it in a non-adiabatic way with a Hamiltonian that does not commute in different times. So we will have a lot of transitions. And then we will have, during the dynamics, a kind of quantum fluctuations, and also as the initial state could be, for example, an equilibrium state, we also have thermal fluctuations. Okay, and the typical scenario that we have is a system that we drive using some external parameter, like we change the field. And the system is also, in the lab, the system is always coupled to the reservoir. If you do the drive in a fast time scale, there is no time to exchange a principal energy with the environment, and then we can describe that dynamics as a unitary. So what is work? Work is all process that does not involve variation of von Neumann entropy. What's heat is the process that involves variation of the von Neumann entropy. And this definition is in the Kittel textbook, the thermal physics. So when we have a process where we only drive the Hamiltonian in this fast time scale, all the energy change will be work. We can do it adiabatically or not adiabatically. all energy change will be work. And when we let the system thermalize with the environment, all the energy change, the von Neumann entropy will change, and all the energy change will be heat. When we have the buff process at the same time, it's a little bit trick how to measure that things and how to separate what is the contribution of work and what is the contribution of heat. There are some formulations and some methods to measure it in the lab. And okay, we are far from equilibrium and we have very small systems, so fluctuations are important. And what we use to theoretically describe that system are the fluctuation theorems. The fluctuation theorems give us the framework to treat that system. For example, when we vary the Hamiltonian of the system and let the system to a non-equilibrium state, the probability distribution for the forward process, for work in the forward process divided by the probability distribution for work in the backward process satisfies this equality. And this encompasses the second law of thermodynamics. So this is a kind of a generalization of the second law that will give us a lot of limits in quantum technology. I will try to convince you about this. And oh, yes. Sorry? Yes, this is the Jarzynski. When it's well, it okay. This is the Jensen's from we have an equality for the exponential of work and for the exponential of the variation of free energy, right? It seems to be not very useful because it's about the fluctuations. It's about the explanation does not gives you much predictive power. For example, like the second law of thermodynamics. Yeah, yes, the red arrow is to obtain something which is similar to the second law of thermodynamics. As we have a convex function here, we can use the Densing inequality to show that the mean value of work minus the variation of free energy, Helmholtz free energy, it should be uh, greater than zero, as we have that equation. No, yeah, we have equality for the exponential, and then when we go to the thermodynamic variables, we recover an inequality, right? But that thing is useful, and I show to you why it is useful in the experiments, and also to make predictions, and also to project a maximum demon, and also to design a protocol that we can have advantage in the quantum scenario. And what is the typical process that we can do when we drive a system? A similar thing of compression and expansion of a piston. We can increase and decrease a magnetic field. And here I have just a spin and a half. We can also do things similar with harmonic oscillators, as Marcos commented yesterday. And for example, if we increase the intensity of the field, we will open the gap of the system. If we also change the direction of the field, we will produce transitions between ground and excited states and so on. Okay, so the first thing that we have to do in order to access the thermodynamic variables in that system, how much time I have? Okay. So the first thing that we have to do is to measure such fluctuations, and it's not an easy task to do. And if you want to verify experimentally, sorry, there is a minor signal here. And if you want to verify a fluctuation theorem like this one, we have to measure the probability distribution for work, heat, and so on. We have to measure fluctuations. The first verification of this theorem in a classical system was made in 2005, studying um, um, folding and unfolding of proteins. And in the quantum domain, this was the first verification of a fluctuation theorem. The experiment was performed in Brazil. This is a collaboration among people from a lot of different countries, but the experiment was performed in Brazil. And we use it here. I'm not entering details, but if you want later, we can discuss the the good and old Ramsey interferometry. So we based our protocol in the Ramsey interferometry that we used to use a lot in quantum optics. And the idea is instead of measure directly fluctuations, we measure the Fourier transform of the distribution. So we are measuring the characteristic function, and we have all the information about the distribution in the characteristic function. So we transform uh, the statistics measurement in a measurement of oscillations, and then taking the inverse Fourier transform of the experimental data, we recover the distribution. Of course, in the theoretical description, we have delta functions, and in the lab, what we have is a Lorentzian function, depending on your temporal resolution. So, okay, we are able to access these fluctuations, and then we can verify this kind of theorem in the lab. And we can see that if you plot the data of the fluctuations in the logarithmic scale, we can measure the variation of free energy. So we can now access, this is for the best of my loaders, and also I think in chemistry, there is no method better than this one to measure variation of free energy between two configurations of a system. And also we have a measurement of the temperature because the slope of the curve depending on beta. So here we have a kind of a thermometer that has resolution of just few nanokelvins in our experiment. So we can do it for a cycle. This is the work distribution in a heat engine. We can do it for a refrigerator. We can do it for heat. And we also know how to do it in a many body system. We performed an experiment with just few body in a small interacting spin chain, but we have a general recipe to measure fluctuations for a many body system also. It's a kind of very demanding experiments because we have to prepare a state in different temperatures, and you have to measure also different observables, but we can reconstruct the distribution, and we can test and verify these fluctuation theorems. So the next step is understand uh, in a deep way irreversibility in our system, in our molecular quantum processor. For example, if we quench the system, if you change very fast the Hamiltonian, there is no time for the system change the state. And if you do a quench not very fast, for example, here we are changing the field, the magnetic field, along the plane from X to Y or from Y to X, and we are also changing the intensity of the field, and we are looking for one of these nuclear spins. And we are performing quantum state tomography along that evolution. So this representation in the block sphere are a representation of the experimental data. This is not a theoretical calculation. And when we do it very fast, compared with the energy gap, we have to compare the frequencies with the energy gap, right? We have a kind of nonlinear response. When we start to do it slowly, the system approaches the linear response regime, and we can see that the forward dynamics becomes very similar to the backward dynamics. And then we can write formally in this unitary driving followed by a thermalization. The entropy production can be written formally as the Kubock divergence between the density operator in the forward dynamics and the density operators in the backwards dynamics, the time reversal process. And then the divergence, it's not a distance really, but I will say the distance between the two trajectories is associated to the entropy production. When we are near to reversibility, we are near to quasi-static protocol, we cannot distinguish between these two trajectories. So the distinguishability between these two trajectories in the Hilbert space are associated to the irreversibility. And when we do it, we can separate the entropy production in a kind of a quantum friction, which is associated with co-coherence, and also a residual lag, which is associated to a variation in the Hamiltonian. So even when we do in the quantum adiabatic way, we have a residual lag. Okay? So a quantum adiabatic evolution produces entropy. This is an important thing that people have to know. So the APS said in this very nice viewpoint that nuclear spin points out the error of time. So Vitor, let's see if you can back to the dinosaurs. So one of the first attempts to challenge the second law of thermodynamics was introduced by Maxwell in this tale about the Maxwell diamond. And I think every physics and also Arthur Eddington uh, point out this. In general, we think that the second law holds a kind of a supreme position among the laws of nature. So anyone can propose something that goes beyond the Maxwell equations or goes beyond quantum mechanics or goes beyond the standard model, but no one can propose something that goes against the second law. So Eddington thought that there is no hope if one propose something that goes beyond the second law, but to collapse in the deepest humiliation, right? So I will take my chance and I will try to convince you that we can go beyond. Actually, we have experiments. Yeah, sorry. Uh, uh, but with comment, which one? Yes, exactly. Yeah, exactly, exactly. This is a very yes, yes. This is a very general theory. This is completely different from any other theory. This is not algorithm. Okay, this is really general, but this is still general in the quantum domain. So here we have the Ziller's engine, and Solomon told me in the morning, in the yesterday morning, that it seems that Ziller had this idea during an Einstein course about thermodynamics. And so the idea is to have an intelligent being that here I have ideal gas of just one particle. This is a Gedanken, right? And this intelligent being is able to introduce a division in this compartment. And then if the particle is on the right side, he will attach weight in the proper side. And then he can instruct in the isothermal expansion of this thing here, KBT ln of 2 of work. But we know that Hoflandauer said that information is physical. So information is registered by a physical system, and the daemon must use at least one bit of information in order to in order to measure which side the particle is and take the decision. And we have to erase the daemon's memory in order to perform this in a cycle. And the amount of energy that we dissipate when we erase memories at the minimum, if we adopted the Landauer principle, is KBT ln of 2. So there is no free lunch. But that's okay. This is the exorcism of the Maxwell daemon. But we can also describe the daemon. It's not necessarily to exorcise the daemon. We can describe the daemon as a feedback mechanism in the modern way. And we can describe the possibility to access the microscopic degree of freedom. And when we do it, we end up, actually, Sagawa and Ueda ended up with this fluctuation theorem where we had work, variation of free energy, and a mutual information density, which is this quantity here. Taking the average of that quantity, we have the usual mutual information that we use in information theory. So if we have a kind of the demo is a kind of a feedback mechanism. Here we have a measurement, and here we have a control. And the mutual information measure the correlation between the measurement and the control. And when we use this, using the Jensen's inequality again, we obtain another generalization for the second law, where the entropy production, so we are updating the Clausius formulation of the second law in the presence of a daemon, and the limit for the entropy production is negative, and it is equal to minus the mutual information. So this is the best that the daemon can do to decrease the entropy of the system, right? So we have a cost to put the daemon there. Yeah, but if you think that the daemon is a extra resource that we have in the quantum domain, we can do something which is better than what we have in the classical domain, right? This is the first implementation of a quantum daemon. There was some implementations in classical systems, but this is the first one where coherency is important. And we can also obtain a equality for entropy production. So this is a equality for the second law, valid in a kind of general scenario. So here, the daemon can perform projective measurements or something close to a projective one, and the unital process. So it's more general than unitary, but this is not a general process, process that preserves identity, like dephasing plus unitaries. And in that case, the entropy production will be equal to information gain. So in one side we have thermodynamics, in the other side we have information theory. We have information gain, which is a negative, it's negative here, and some positive terms. A mean value of a Kullback divergence, a relative entropy, plus a variation in the Von entropy. So depending on how we organize the process of the daemon, we can reach a negative entropy production situation. And this is the measurement of this negative entropy production situation. But the bound, the mutual information bound that we obtained in the fluctuation theorem is not tight. We cannot achieve that bound, at least with this kind of daemon. So this is an open question, if is there any kind of daemon that can achieve that bound, or if you have to improve the bound. But we have equality, at least for this kind of protocol. This is valid for any size of the system. We performed an experiment with just qubits, but this is valid for any size of the system. This is valid for harmonic oscillators, for a chain, for a mini-body system, etc. So this is the first generalization of the second law. And now, in the news, people said that we are now inside of the Maxwell daemons. So let's go further a little bit. And we can also test, as I told you, the fluctuation terms are a kind of generalization, are also another way to state the second law, but for a very far from equilibrium system. And we have to test it in a feedback protocol. So in that case, we will have a kind of plane, and the ratio between the forward and the backward version of the protocol, of the daemon protocol, should lie on a plane. And we obtained this just a few months ago in the lab, and this will be reported on arXiv at some point. I have also to compute the error bars here, but the points are really, really over the plane. You can believe me. And in one axis we have work, in the other axis we have this mutual information density. And this is what we measure. I am not entering the details, but this figure here is a representation of an experiment that took several hours. And we can also obtain the variation of free energy in this context. And there are these there are these thermodynamics uncertainty relations that people obtain directly from the fluctuation, that can be obtained from the fluctuation theorem, but there are people obtaining this from other methods. And this is again another way to talk about the second law. This tells you how the fluctuations of your system is limited by your entropy production. There are relations with for work, for heat, and also for other things. And we see that for a feedback mechanism, the standard relations are violated in the same region where the daemon could challenge the second law. Okay, it's a kind of a apparent violation of the second law because we can use Landauer in order to establish the second law. So a few years ago, actually 10 years ago, when Lucas was in Santander, we obtained that relation for a limit in quantum metrology associated to the entropy production. So when we perform our quantum metrology protocol, we always start from the thermal equilibrium, then we prepare the probe, then we let the probe interacting with the system that we want to measure. We encode somehow the variable that we want to measure, let us say this phase here, and then we have a measurement strategy, an interferometer, for example. Uh, your in the real world, your system will produce some entropy because you don't have perfect unitary evolutions or perfect state preparation or perfect driving of the system. And this entropy production limits the precision of your measurement. So, but at that time, we did not call this as a thermodynamic uncertainty relation, but we obtained something like this before people start to talk about this. And people don't cite that paper. People should cite that paper, right? So now, one of the motivations that I start to study this was to perform an experiment to test this fundamental limit for for quantum metrology. And Lucas, now I think that I have the tools that I need to test it after 10 years, finally. And okay, let's see if we can challenge even more the second law without using a memory. So there is no way to exorcise this kind of thing using Landauer, for example. When we start with a system which is correlated, we can see some unusual heat flow. For example, we can see heat flow from the cold to the hot without expend any energy. Okay, this is a kind of not spontaneous because we have to prepare these initial states, but this is cost not costless because uh, we have the cost of preparing a correlation, but there is no energetic cost to perform refrigeration in that scenario. So people was proposed this using entanglement, but in our experiment we don't have entanglement. We just have coherence in the correlations. And so we start the heat transfer at the very uh, uh, basic level. We have just one nucleus, one cold and other hot. Then we let the nucleus interact in a thermal way. And in the end of the day, we will have the two nucleus in a warm state. This is the usual second law. Heat flows from hot to the cold spontaneously without performing any work. But if you start with a very special initial state, and depending on what is your interaction here, we can observe this unusual heat flow. And people associate the thermodynamic error of time with entropy production. And if you revert the entropy production, we are reverting the thermodynamic error of time, not time itself, just the thermodynamic error. And again, using information theory, we can obtain an equality for heat exchange in terms of variation of mutual information and also Kullback divergence. And this is the entropy production actually in the protocol. And we have a kind of a trade-off. And we have necessary insufficient conditions for this unconventional heat flux for qubits. I'm okay. So I will try to finish very fast. So these are the experimental data. We can see one system becoming hotter, the other one becoming colder, and the connection with the Vitor's tale in the beginning of the conference is this one. A journalist of the British News of the Times said that about this work. The time really can flow backwards, but don't blink or we will miss it because it is very fast, depending on the time that we consume the correlation. So, but unfortunately, time itself didn't flow backwards. We are talking about spontaneous reversal of a process in time. It's not really uh, 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 a time reversion. And also, science fiction used this. So I will jump just to 1 minute, 1 minute, right? And the third law, which is a very fundamental limit, is associated to the fact that all variations in entropy goes to zero when we go near to zero temperature, right? Nernst formulated this heat theorem avoiding the concept of entropy. He said that when you approach zero enthalpy and the variation of Gibbs free energy are equal, and also the variation of your internal energy and Helmholtz free energy will become equal. This is a kind of figures that we can find in the original Callan work and also in the textbooks, but there is no experimental data to validate that figures. And now I will not tell you how we measure it, but I will show to you this is the validation of that figure. So we can see that when we are going very near to the zero temperature, the variation of the energy and the internal energy become equal, and the variation of entropy in the protocol also goes to zero before to reach the zero temperature, and also oh, and also the same happens for enthalpy and Gibbs free energy, and the consequence is the heat capacities goes to zero. So there is no way um, to take out the entropy of the system and to reach the absolute zero. So the consequence is the unobtainability principle, right? And now we have an experiment very close to zero. How close to zero we are? The effective temperature of our magnetic system is about 4.8 nanokelvin, and we are trying to improve it a little bit. But there are several open questions about how to test these, etc. The only final message that I want to say is hope did not collapse in the deep simulation according to Sir Arthur Eddington, but it is up to you. And we had a lot of collaborators that I had not time to thank. And in Santander, we have some playgrounds for quantum experiments with nuclear spins, twin photons, exquisite light, and we are building trapped ion with terbium, but we're still building this. So if you have any out-of-the-box idea or even crazy idea for an experiment involving few qubits, we are more than welcome to visit us and to propose something. Thank you very much for your attention.